Alrighty. Well, welcome to Fluids. Looks like people are in the right spot. That's good. I think I know everybody, which is kind of fun. So I know you guys know me, had me, most everybody last semester. So this should hopefully feel similar-ish, at least in how the course is run. But obviously, we're not taking thermo again. We're taking fluids, which is unfortunately a little bit related to thermo. So we're going to have to do energy balances at some point, and it'll be lots of fun. So how these things kind of fit together, can put this up. So I know some of you are in fluids. Obviously, that's what we're taking now. Some of you are also in heat transfer. I think almost everybody just took thermo. These things are all kind of part of the same larger, what we call thermofluid sciences. So they all have pretty significant overlap. If you're taking like fluids, and for the couple of you that are also taking heat transfer, especially later in the semester, you'll be like, we're doing the same thing in both classes. All of these areas share quite a bit across, because you need to be able to, if you want to understand how fluids move and behave and flow, you need to know how energy works in those systems. So you might need energy balances. And if you want to understand how heat moves in fluids, you have to also understand how fluids move and behave. So there's a lot of crosstalk between all of these different areas. No, rats. Ignore. Start working. Don't hit the wrong button. Okay, cool. So if you want to kind of know where some of this stuff might show up, maybe you'll find something that's kind of interest of you. We're obviously going to touch in little bits and pieces on a lot of these areas. Obviously, one place that you think of when you think of like how do fluids behave, why do we care about this, is in the aerospace industry. So if you want to look at rocket engine design or airplane wing design, you can see maybe next time you're on a flight, look out the window if you're by the wing, and you'll see out on the edge of the wing these little sticky up things. Why are little sticky up things on the edge of the wing? Well, it's to control boundary layers and basically prevent your airplane from falling out of the sky. So they're kind of important, just these little kind of funky fin things. We'll learn about why those are there, why you would want something like that, and how some of this stuff works and behaves. If you're a civil engineer, then typically you're not looking at airplane wing design, but you're looking at how fluids flow in, say, a water supply and distribution, or a drainage distribution, or you want to look at how water exerts pressure on something like a dam, or in a system like that. So we're going to learn about things that are kind of related to those types of applications. If you're a mechanical, lots of different things in mechanical land that have to deal with fluids and how fluids behave. So obviously aerodynamics is part of it. If you're in the auto industry, you're looking at not only the aerodynamics of like a full-size car, but you want to understand, how do I build a model car and test aerodynamics on a model car and then scale that to a full-size car? It's straightforward, but there are some tricks that you need to do to actually be able to scale systems from model size systems to full-size systems. You might be looking at how to design an HVAC system for a building. Any of you that live in Collin Hall know that's apparently not the world's easiest thing to design an HVAC system. That's like not the worst thing ever. Collin Hall is particularly bad, but lots of the buildings on campus, you're like, oh, it's boiling lava hot in this room and it's freezing cold in this room. It's not that easy. You really have to know a lot about how fluids flow to be able to design that well. And then the one in the bottom left is a power plant turbine for a hydroelectric power plant. So something like that, you need to look at how fluids behave, how fluids move to be able to design something like that. Where else? If you're a chemical engineer, chemical engineers, often you're looking at fluid flow problems. Sometimes the kind of top left one is what we would call microfluidics. So sometimes it's actually beneficial to be able to scale things down, especially for diagnostics. So there's a whole area of chemical engineering centered around medical diagnostics. So how do you do really rapid screening for, say, blood tests without taking a whole bunch of blood from your patient? So you want to scale the system down, scale the analytical techniques down, but still understand, you know, how do blood cells flow through these little small channels? And that's an important part of, like, how do you actually design these systems? Whether it's a medical test or something like that, where it's a picture of mixing probably two fluids with food coloring in it, you know, for the cameras. But you might do that scale. You might also do really large scale, shown in the bottom, that, you know, maybe 100-foot tall distillation columns. You really need to know how fluids are behaving in those columns. You have both liquids and gases. A lot of times the behavior in those systems is quite complex. This purple and yellow thing in the bottom left is what we call a flow battery. So those are starting to become, so we're looking at different larger scale, lower cost energy storage technologies, especially for the electric grid. There are a number of companies looking at commercializing what we call flow batteries, where it's a battery sort of, but you have, instead of having like a fixed kind of two metals as your cathode and anode, you have two solutions as your cathode and anode. And looking at especially high power, if you want to discharge this really fast, you have to look at how ions are flowing and moving in the solution, and look at the kind of the fluid aspects of now this battery system as well. Okay, what else? Biomedical. You're looking at designing an artificial heart. If you're looking at how blood flows through the body, if you're looking at how arteries and veins could clog, you're looking at any of those kinds of things where you're looking at fluids in the body. That's obviously something that fluid mechanics, some of the aspects of fluid mechanics are going to be important. And I think all of you have played, will play, still do play some sort of sport. And there are kinds of fun applications. We'll touch on quite a few of these throughout the semester. Like, why is a golf ball shaped? Why, when you watch people in the Olympics in like a road bike race, they have these really goofy helmets that have like a big point on the back? Why do we make helmets like that? Why is, you know, how do you make kind of a more aerodynamic race car? Or why, when you look at anything that's like aerodynamic or streamlined in shape, it's like long and pointy at the back end? Or any modern car, they're all like, all of the SUVs and stuff, they're now all sloped toward the back. Why do we design cars like that? So lots of like sports and kind of practical real life applications. We'll touch on different things of fluids that are just kind of weird and interesting, because I think it's fun. But hopefully you'll find at least something that is relatively interesting to whatever you happen to be doing. I know there are a bunch of us here that have a lot of different interests. We'll try to kind of touch on a bunch of those here in fluids, because I think it touches on a lot of different things. Okay, so we're gonna start, because you've all had me before, we're gonna push off some of the discussion of how the class works till Wednesday, because it's Monday and you probably have heard that at least twice already. So we'll push that off till Wednesday. The class is basically going to run similar to thermo. If you just took thermo, you'll kind of be in the groove. We won't talk too much about that. So instead, what we'll do today is watch some videos, because videos are fun. We'll try to watch a lot of videos in fluids, because to be able to visualize fluid behavior, which is a lot of what we're doing, you have to watch it. It helps to watch it. So we'll try to watch a lot of videos. And then we'll also try to connect like the math of what's happening to the kind of visual physics of what we're seeing in some of those. And then some we'll watch just because I think they're kind of fun. So we'll do that a little bit today. But before we do that, we're going to start with kind of a couple kind of high-level things that will set us up for the rest of our semester discussions about fluids. So there are a couple of kind of key things that we are going to take really for granted about how fluids behave that are not exactly true. And we're going to spell them out now because they're not exactly true, but they will be true most of the time. So it's useful to use them as assumptions. So I guess we'll start with first, what is a fluid? Kind of easy thing. So liquids and gases. So we have solids. We deal with those in like a mechanics of materials type class, or statics, or thinking about that. We use some of the same some of the same terminology in fluids, like a stress. You can have a stress on a solid. You can have a stress on a fluid. But obviously, things like liquids and gases behave really differently than solids. There's some overlap between those. So you can have something like shaving cream or whipped cream. Like, what is that? It's kind of solid until you push on it, and then it's liquid. So there's this whole kind of class of things that are maybe, did anybody play with oobleck in like middle school? So oobleck's a fun one too, because it's like if you push on it gently, it's liquidy, but if you push on it really hard, it's a solid. So it's like flipped from shaving cream or whipped cream, or Jello. Like Jello is solid, but if you push on it, it's definitely liquidy. It yields fairly easily and then has kind of flow type properties. So in a fluid, we'll start with kind of a simple definition. So what is a fluid? It's going to be a solid. Sorry, not a solid. A liquid or gas. It's not on the screen. It should be on the screen. It's on my screen. Be on the screen. All right. No, don't do that. Sorry, guys. Amateur hour over here on the screen. Still not on the screen. Duplicate. Go. It did, and then it changed my settings. Oh, fine. All right, give me a second. How do I do it? No, duplicate. Do that. Yay. All right. Okay, so what is a fluid? So a fluid is a liquid or a gas. Right, big news. Fluids are by nature discrete, so they're made up of individual atoms, but we are not going to treat them that way. So they're discrete. But we will treat as continuous. So in a real fluid, like the air in this room, if I take a chunk of air in this room, there is some discrete number of atoms in that air, and I could use the amount of atoms in that air to calculate a density. And if I took another chunk of air somewhere else, there's going to be a slightly different number of atoms there. So I'm going to have a slightly different density because they're maybe a little bit, a couple more, a couple less. But we have the large numbers, so it's going to be very, very small. So in practice, most of the time, fluids are continuous. If I take a chunk of air from right here and a chunk of air from right there, they're the same density, they're the same properties, same viscosity, because they have the same number of atoms, at least pretty close. That assumption will start to break down when you get to systems that are like really, really, really low pressure. So if you only have like, I take a chunk of air here and there are 4 atoms, and I take a chunk of air over here and there are 6, all of a sudden maybe that matters for what you're doing. Those are pretty weird conditions for like normal life. The other place where that breaks down is if you go to really, really, really small. So if you start to try to understand fluid behavior on like the nanometer scale, where like atoms are not infinitely small, but they're like big, then that starts to break down as well. We're not going to go that small. So for practical purposes, for like macro scale, everyday object size things, fluids are continuous. It doesn't matter. Fluids are continuous media. We don't have to treat them as individual atoms. So we will pretend that they play nice, like we can take a differential of a fluid, right? You can't take a differential of a discrete function. You can take a differential of a continuous function. So we're going to pretend fluids are continuous, and we can do things like calculus with them. And for most situations, obviously, we can. Okay, so what that means, we have like a set of properties. So they're continuous. We can kind of play nice with math, but then also like at any individual point, we can kind of define our properties, like a velocity or a density or a temperature. Lots of these, we can define them at every individual point. We're not going to like have a piece of space that doesn't have anything in it, like, because it's continuous. So every space has something, and we can kind of tell all of the different properties at every point. Long way of saying they're going to play nice. We're going to be able to do calculus type math with them. So that's going to be one of the shifts that you see in this class versus like what we did in thermo. We're going to have more calculus in this class. We'll try to keep it. We'll try to keep it in check a little bit, but some of it we kind of have to do the calculus. Some of it we'll do some of the calculus at least in class to be able to show how it works, and then maybe not as much of it in homeworks or on exams, but we'll definitely have calculus kind of sprinkled in throughout. We'll even get to some kind of fun differential equations type stuff, at least for a little bit. Okay, so fluids play nice. There's kind of a wide range of ways that we have to look at fluids to actually be able to analyze them. So this is where I think this class is kind of fun, because it sees a whole bunch of different physics kind of coming together to try to explain fluid behavior. Fluids often do things that aren't really intuitive, but it's kind of the combination of a whole bunch of different ways of looking at it. So we analyze fluids with a whole bunch of different methods. So, okay, so one physical law that we're going to use is conservation of mass. So if we want to understand how fluids flow and move, they have to obey conservation of mass. All right, what other kind of physical laws like that might you think come into play in fluids class? Things that you've learned in like other engineering classes or physics class or something like that.
Conservation of energy.
Conservation of energy, wonderful. If we didn't get that, I would have been sad. if you want to understand how forces work in fluids, like if I push a fluid, what happens? What physical law? Newton's first law. Okay, what other one? That's the good friend of Newton's first law. Newton's second law, which is what? So Newton's second law is one that we're going to use a lot. What's the kind of more colloquial, if we don't remember what Newton's second law is? Force equals, yeah. Okay, what's the very good friend from thermo of conservation of energy, or the first law of thermodynamics? Second law of thermodynamics. You lost it. Oh, I think I lost my sharing. Give me a second. Okay, so Newton's first law, Newton's second law. Second law of thermo, yes, not tons. What if you had a, say, a fluid like rotating or spinning? Is there any like sort of Newton's law type law that deals with spinning things? Torques, yeah, so we'll be calculating torques, but remember there's like a conservation of angular momentum. Right, so this is why when you spin on a spinny chair and you hold your arms out, you go slow and you tuck your arms in and you go really fast, because there's a law of conservation of angular momentum. The total angular momentum in the system has to stay the same. That's one that we won't use too much, but that would be another one. So this would be principle of angular momentum. And then we'll also use things like ideal gas law. You remember that from thermo or chemistry or something. We did in thermal a little bit of like non-ideal gases. We're not going to do non-ideal gas stuff in fluids, really. We'll kind of save that for other places. But we will do some ideal gas law stuff. And we're dealing with real world stuff, so we'll also have to bake in some understanding of physical properties. Like one of the key ones for fluids is viscosity, but also like density and some of those things that you might know already from how we can look at and understand fluids. So just to give a sense of kind of where we're going to be drawing from as we're starting to look at these, the ones that we're going to spend the most time on is, so certainly conservation of mass, a little bit conservation of energy, not much. So I'll star that one. We will spend a little bit of time on that. Newton's second law, we'll definitely spend quite a bit of time on Newton's second law. Basically no time with the second law of thermo. We might mention it. I might never mention it again. It's okay. I like the second law of thermo, but we won't really touch on it here. Principle of angular momentum. We might see that come up a little bit in videos talking about especially like vortexes where fluids start to swirl. We're not going to spend too much time on it. We certainly won't like dive too deep into the math of that. And then we will a little bit ideal gas law and quite a bit physical properties. So these will kind of be our home for this class at least. So we're going to look at conservation of energy, right? If fluids are moving, they have energy. So we want to see what that looks like and where it goes and how we can take one form of energy and turn it into another a little bit. Mostly we'll be looking at like changing from one form of like mechanical energy to another. So we'll look at like changing from, pressure to velocity, something like that. If you're squirting out a fire hose, right, you're going from pressurized fluid inside of your hose to a really fast moving fluid outside. So we'll definitely look at conversions like that. We're not going to be doing like the whole energy balances all the time. There'll be some things where we kind of do those in the background. So it'll show up a little bit more in the background. Certainly not as like all encompassing as what conservation of energy was for us in thermo. Newton's second law, that's going to be a fairly big one for us. So if we want to understand how fluids move, we have to understand how forces work. But then also right, F equals ma is a fun one, and it's really easy when you're talking about like a solid. Right? If I put a force on a solid, it moves, and I can calculate the acceleration, and I know the mass, and it's all easy. But when you're talking about a fluid, if I exert a force on the air, F equals ma still works, but it's super weird because like the fluid, what's the mass? So this is where we have to start getting a calculus description to be able to understand things like that. We're also going to be using some of the same kind of tools that we used for analyzing fluids. So in thermo, we used control masses and control volumes. Those will both show up again. So if you imagine, let's say, get black again. So we're typically going to be looking at control volumes. That maybe makes sense because it's going to be harder to track like an individual mass of fluid because you push on it and it goes all over the place. We will actually do that. It's kind of fun to do control mass analysis on fluids. You basically like track every individual particle. That's the basis. If you ever look at, and we will here in a second, if you ever look at like modeled fluid behavior, it's all based on control mass analysis of fluids. We'll do that actually. So we'll do the math behind how you build up these computer simulations of fluid flow. We won't like do solutions by hand too much. We will a little bit. It'll be kind of fun. But we'll do like the super easy ones where everything is really easy and well behaved. A lot of times we'll focus though on control volumes because it's much easier to define like a set volume and look at how fluid goes into that and how fluid goes out of it, and maybe it changes speed or something like that. So we'll do that quite a bit, right? We could imagine, yeah, kind of a number of different things. So I'm going to pause it there. We'll pick up with some of the other notes, but kind of for the rest of today, we'll watch some videos that I think are kind of interesting. And we'll see if we can actually get it to work with sound. So it probably will take me a second to actually get this working. But okay, so okay, so you can see hopefully Moodle. Okay, so this first one, we'll just watch kind of snippets of it, but this is just so Don Pettit, actually, Don Pettit is an astronaut that spent like a total of about a year in space. And when you're an astronaut, you're typically a huge nerd. And Don Pettit fits that description quite well. I got to see him give a presentation. It was weird. It was in like a little room smaller than this, and there were only like 20 people, which usually astronauts giving speaking events, you get like lots of people in a huge room. So it was kind of fun. And basically he showed videos of all kinds of weird fluid experiments that he did in space because he was in space. And you don't have a lot of things to do in space when you're not actually like doing your job. So you get to sit around and you don't have stuff. You have like water and that's it. So he brought water and you have high-speed cameras and all that kind of stuff. So he played around with fluids and was like the most excited about little fluids in space that anyone could ever be. It was kind of fantastic. So he has a whole bunch of videos online. This one is just, I guess, just to see kind of some of the counterintuitive behaviors that you can see in fluids. And because I like Don Pettit. This is them playing around with it. Those are just air bubbles, but they don't separate because there's no gravity. You'll learn about boundary conditions and how they can influence fluid behavior. One of the fun things. Yeah, you get these kind of weird. Well, I like Don Pettit, but we don't need to listen to him talk so much. You get, I don't know if you saw it in a couple of the, yeah, this is a good shot. So you get these kind of weird spirals, but they don't go like backwards with the direction of motion. They go like toward the direction of motion, which is like backwards to how I would think that they should go. So sometimes you can get kind of weird behavior, especially when you're not experiencing Earth's gravity. Don Pettit has, if you like hearing him narrate his wonky fluid experiments, there are tons of them. We'll look at one more of his because I think it's fun. So this one just I think is a good demonstration of F equals ma in a fluid. So what he has here, what you're looking at is a solid sphere of water, right? Remember, this is in space, so things are fun. So there's no gravity, so you can just like water, it will just form like a huge drop. even though it's like the size of your head. It's just a big ball of water. And then he took a syringe and basically injected air as a bubble into the center of that. And that air bubble stays in the middle because there's no gravity to separate them. So you have an air bubble inside of a big bubble of water because space is wonderful. And then he's taking a syringe and injecting another bubble of water. So this little thing is a bubble of water inside a bubble of air, inside a bubble of water. It's fantastic. And basically what's going to happen is we'll watch kind of as that center bubble of water kind of bounces around in there, what happens. So watch it kind of roll around. And then you see all of a sudden it got smaller. So there's a mass transfer, basically like the water loses some of its mass and then it bounces it and shoots it off the other way. Yeah. They use food coloring so you can see a little bit easier. You see that jet go into the big one, and then the little bubble shoots off the other way. It's F equals MA. Well, kind of wild. So you can do fun things in space if you have lots of time and only water to play around with and syringes. They don't let you take a whole lot of other stuff into space. This is one that's maybe you've seen stuff like this. Get rid of a ad. So this is an ad for an aerodynamic kit for a semi truck. Maybe you've seen stuff kind of like this on semi trucks driving down the highway. You've seen ones where they have like the skirt along the bottom, which maybe makes sense why that would give you better aerodynamics. But then sometimes they have like big flaps or something kind of on the back side of the truck. This is an advertisement for a kit like that. So when you look at a simulation like this, where you see like those lines or the particles that we just saw there, all of the actual physics that's underlying those computer simulations, that's what we'll learn about, and we'll learn like how do you actually build a simulation like that. If any of you do fluids in the real world, you'll use simulation tools like that. So we'll learn kind of how do those actually come about, what's behind all of that. But just to point out kind of what the simulation results would look like. All right, we don't need to contact them. Some kind of terminology and things like drag and injecting accelerated fluid into the low pressure wake and all sorts of stuff that you'll know actually what all of that stuff means and why it works and why we do things the way we do by the end of the class. The last video that we'll watch is kind of a comparison between what we might see in an experiment and what you might see in kind of a simple computational model. So the computational models in fluids are really, really valuable. But one of kind of the key challenges is fluids are really hard. And when we try to build up computational models, there are kind of assumptions that we make that are not true that can sometimes, we can capture the big picture, but it's hard to get at all of the results, all of the kind of fine detail of results. So fluids is kind of one of these areas that we use a mix of computational and experimental work to be able to actually understand it, right? You've all seen pictures of like a car being tested in a wind tunnel or something being tested like that. The reason we have to do wind tunnel tests is because our computational methods aren't good enough to be able to get all of the information we need. You'll see that a little bit here. So we're going to look at what we call a cylinder and cross flow. After we learn about tacos. So this very exciting video. Just to describe what you're looking at. So you see it's a chunk of PVC pipe. You're looking at it down the end. So you see just that cylinder side. And they have holes drilled in the top and bottom where they're putting smoke out of the top and bottom of that PVC pipe. And then from left to right, there's a fan blowing. So there's air blowing across that thing. And you're kind of looking at what is the wake that forms. You're all familiar with like the wake behind a boat. If you have something, fluids flowing over an object, a lot of times you get a wake. Why exactly you get a wake, we'll talk about. You know, what's happening in the forces in the fluids and why you get a wake forming, and is that good or is that bad, or, you know, what do we do about that? But you'll be able to see kind of with the smoke on the top of the bottom, what's actually going on in the wake behind this cylinder. We call it a cylinder and cross flow. This is kind of a classic geometry where you have a cylinder and you have fluid flowing across it. Okay, so you see those vortexes that are forming. So you see the swirls, and you can see it's kind of like a pulsating thing where you see like a cylinder form or a vortex form, and then two vortexes form and two vortexes form. That's kind of a classic result. If you change, no, not that. I didn't want that. I want to go back here. So if we changed the velocity of the air, we would start to see different effects. So if you made it really, really fast, then it would just be all swirling and mixing behind it. If you did it slow enough, the fluid would actually like slip kind of cleanly across it, and you wouldn't have any wake at all. If you were kind of in the middle, sometimes you can get not the two vortexes forming at once. You can get like forming kind of alternating top and bottom. So you can get lots of different fun things. This is the attempt at a simulation. This is kind of it's a fairly coarse-grained simulation, but a computational simulation of a system with the similar dynamics. So you can see we're kind of forming similar-ish vortices. So we get kind of the big picture right, but obviously we're losing a lot of detail in this simulation. We could do a better simulation. You can kind of always do a better simulation. Making a better simulation is going to take more time or more computing resources. So we're always kind of trying to balance, like, you know, how do we do that well? I don't want that. Okay. Yay for autoplay. So couple videos. We'll go over the syllabus on Wednesday and how the class works. just kind of the high level stuff. It's going to be sort of like thermo. We're going to have homeworks typically due Fridays. So that will be kind of our regular cadence. We'll get our first homework will be assigned this coming Friday, due the next Friday, and we'll kind of largely try to stick with that through the semester. But we'll end there for the first day and come back and talk about fluids and how they behave here again on Wednesday. So I hope you guys have a good first day. Enjoy the sunshine. Enjoy not having like full on class quite yet this first week. We'll see you back Wednesday.